Great, thank you all for being here, and as mentioned, first slot straight after lunch. It's good to see so many faces in the audience, except at the back. I'm here to talk to you today about Mad Monster Standards and my exploration of Webauthn. So first up, who am I? My name is William Brown. I'm a senior software engineer at SUSE Labs. In my day job, I professionally developed the 389 directory server, which is one of the major open source LDAP servers, which is better known as part of FreeIPA, sold by Red Hat, other companies such as SUSE as well. I'm creator of a couple of other identity projects, and I'm the author of the Webauthn library for Rust. And for anyone who is watching this stream online, I'm based in Brisbane, Australia, which means that my time zone is UTC +10. So the best way to get in contact with me if you have any questions after this is my email, wbrown@suse.de. Yes, I'm originally from South Australia. That's why iced coffee is the favourite drink. Well spotted in the front audience. The heckling division is already going off. All of us are used to probably seeing a screen that looks like this. No, I did not just lock my laptop. That's been asked. We're all used to this, which is a username and a password field. And this is how many of us have authenticated and identified ourselves to our personal machines, our corporate machines, and many other things. The username and password was first used in a computer system in 1961 in MIT's compatible time-sharing system. And since then, the password really hasn't evolved much. We've certainly got a lot better in terms of asking things like about password quality and length, but it hasn't really changed much as a technology. And this is really interesting because the attacks against passwords that we see today have evolved so much. And as Alex Weinert from the Microsoft Azure Active Directory team in their really excellent blog post, Your Password Doesn't Matter, has documented, these days, even the rules that we have around your password quality do not prevent an attacker from being able to gain access to your systems, because in many of these attacks, the exact content of that password is known. And so really, passwords are starting to kind of lose out in much more modern security scenarios. So this is where we've seen the rise of multi-factor authentication. So from about 2000 with RSA secure ID tokens, and a bit more publicly available with things like TOTP and HOTP being developed in 2011, such as FreeOTP app and things. These tokens print out a 6-digit code which changes about every 60 seconds or so, and the counter is continually advancing and changing, which helps to add a source of entropy so that even if you know the password, you also need this second dynamic factor, which is always changing to authenticate. And this really helps with many of the attacks that we have today. It really helps in terms of credential stuffing or breach password replays and things like that. But it still doesn't prevent everything. Phishing is still a major source of compromise in organizations, and especially now with real-time phishing capabilities, even TOTPs and other tokens like this can still be phished, and accounts can still be compromised. So we really want to get our authentication to a point where none of these attacks are possible, and these things, we close off a lot of these attacks. What we really want is cryptographic authentication. This is where we have an identity who has a private key and some piece of data, and the service they want to authenticate, which holds the public key. Given the private key and that data, we can create a signature through a signing operation. Given the signature and that same data, the public key can verify that only that private key could possibly have made that signature. In reverse, just knowing the public key is not sufficient in order to recreate that signature even when you have that data. What would be even better is if this private key was in a secure, tamper-proof environment which could not have that key disclosed, removed, or compromised in any way from our machines, even if the hardware is somehow compromised. Thankfully, we live in the future. We already have these keys. We've had these since 2013 with Apple's Touch ID, U2F from about 2014 through things like YubiKeys, and also through the standards that Microsoft has been advancing with their Windows 10 hardware guidelines. Many more laptops have TPMs in them, especially since things like Windows Hello from 2019 with their enterprise support. So we're really starting to see that all of these different types of cryptographic hardware exist. But for us to integrate with all of these different types of cryptographic hardware is very difficult, and that's a lot of developer time to understand and interact with all of these. This is where Webauthn comes in. Webauthn is considered the future of authentication by companies like Apple, Google, Microsoft, and many more. All of these companies are supporting the development and the progress of this standard. And the way that this works is that we have a client, which is more commonly known as a browser or a user agent, which communicates to a web server or an auth provider, and which we are going to call a relying party as part of the standard via Webauthn. And then this allows the client to negotiate over various protocols to various classes of hardware authenticators to perform these cryptographic operations. So let's show you what that user experience is going to look like. So on the left, we have a fully updated new version of Chrome. On the right, we have the YubiKey manager. So what we can see is that when we insert the YubiKey here, you'll see that it comes up on the YubiKey manager. It doesn't have a pin set. And you can see that it matches the device that we've inserted. What we can do next is we can register this device to our account. So we begin the registration process. So we enter in our username, and we select that we want to register this Webauthn device. What will happen is once we've selected register, we are prompted to interact with our key, and you can see that it begins to blink. We touch it, and then we say to the website that we allow to see our identity, and we've now registered. And that's really important, that physical touch. The signing process of this private key can only occur if the physical interaction with that token occurs. This cannot be manipulated via the USB bus. It must be physical presence to perform this. The authentication process is really similar again. Put in the username, and again, we hit login, and the device will begin to blink. We interact with it, and we've now authenticated. And this is such an amazingly simple process for so many users. Like, this usability for so many classes of humans to be able to interact with and gain strong cryptographic auth with such a simple mechanism across a diverse range of hardware authenticators is really powerful. And this is why so many people think this is the future of authentication. But to really understand how to use Webauthn correctly, to attack it, defend it, we're going to need to dive into the details of this standard. So here's some light reading for you. This is the Webauthn Level 2 release. It is 164 pages long. And I promise you, I have less than 164 slides. So let's give you a quick crash course as to what the content of those 164 pages has. So the first thing that happens is our client is going to initiate to our relying party that we want to register a device. The relying party is going to send back that we want some credential creation options. Now, this is tweaked for clarity on the slides. This isn't actually what it's going to really look like. This is just to help with communication. But there's a lot of things going on that is sent back to our client so that it can begin this registration. We're given a relying party identifier, which is who we are trying to register this device to. We are sent a randomized challenge, which is a set of bytes which is going to eventually be signed that is now known to both the relying party and our client. And this is what prevents replay attacks against our registrations. We can request different parameters about our credentials. We can say we only want, say, ECDSA. We could say we only want RSA. We can have rules around what cryptographic algorithms we want our hardware authenticators on that client to support. We can exclude a set of credentials from participating in this negotiation. We can have different types of authenticators selected. So for example, we can request a platform authenticator, which means that it is an authenticator that is inseparable from the device. This is things like Touch ID or an Android Secure Enclave. A cross-platform authenticator is one that can shift between platforms. So things like a YubiKey, things that you can disconnect and plug in elsewhere. And we can also request user verification. User verification has 3 different levels. Discouraged means we don't want user verification. So all this means is that someone has to interact with the device. So that just gives us the assertion that a person has interacted with this device. At the other end, we have required. This means that not only does someone have to interact with that device must succeed on, say, a biometric test or the entry of a PIN or something like that. So we're now asserting that an exact person is probably the one who is interacting with this device right now. And in the middle, we have the default option, which is preferred, which is try user verification if we can, but if the device is unable to offer it, skip it. Finally, we have attestation. This is about what information should the authenticator tell us about itself? Where are you from? Who are you? Things like that. So now that we have these options in the client, we can begin to set up so our authenticator can sign things. And we take a bunch of this data, And what we do is we take, say, the relying party identifier and these challenge bytes, and we take the domain name as the client knows it. This is called the origin. And this domain name being brought from the client only is really important because this is what prevents phishing attacks. Because as we're going to be signing the domain name as the client sees it, it means that we must be on exactly this domain that is wanting this registration or authentication to occur. And so this also won't proceed unless we're on a TLS connection. All browsers enforce this. We collect that up into our collector client data, and we hash all of these with SHA-256. We now take that signed combination of origin, the relying party ID, and the challenge bytes, and then we send that into the authenticator. And that is concatenated with some data from the authenticator itself. And this becomes the verification data. And so from the credential itself, we take its credential ID and its public key. So this is the credential not only signing our origin, those challenge bytes to prevent replays, but also signing its own identity to say, yes, I am actually who I say I am. And this signature process that occurs here, which signs that verification data, this is what only proceeds if the user presence test passes, and if verification was requested, only if that verification test passes. The cryptographic element will not proceed if those fail. Finally, now that we have that signature, we begin to unwind this process and give data back to our relying party. So we take that signature and we also combine it with some other elements from the device, such as the public key, the attestation certificate, which is its chain of trust back to its manufacturer, which we can use to assert the authenticity and the manufacturer of this device. We get the credential ID, and we also get the counter, which is the hardware activation counts of this device, which is always incrementing. So again, we have another layer of replay attack prevention. And all of these are combined with this attestation object. And this is a really scary thing. Like, implementing this was a real fun ride. But the reason this attestation object exists is that it allows us to take many different classes of hardware authenticators, combine it into a standardized attestation format, and then send that to our relying party. So that way we actually can work across many different classes of hardware authenticators. And this is one of those things that really makes Webauthn good, is that use of different hardware authenticators. Finally, we take this attestation object, combine it with our collected client data, and then we send it to our relying party once we've put it all together. That's a weird transition. So finally, we're at the last step of the registration, where now that we've got this attestation, we can send it to our relying party, and it can take its originally offered credential creation options and begin to verify this registration. Now, I've omitted a lot of steps here. If you have a look at the numbers, there's a lot of things missing. These are just a few of the important ones. So we verify that the origin as the client has signed it on that device from its knowledge of the domain name matches what we believe our domain name is. This is, again, that phishing prevention. If the user verification was set to required in our outbound registration options, we verify that the user verification bit in that attestation object is set correctly. We verify that the algorithms in use cryptographically returned from the device matches one of the ones that we actually requested them to use. We assess the chain of trust of that attestation cert, so we want to check that that manufacturer of that device is really trusted and it's not just, YubiKey off the back of a truck which has been compromised. And we also check if this credential ID is being reused on another account to prevent duplicate registrations. And finally, once this is all done, we can register this credential ID and the public key to our user's account so that we can then use this for future authentications. So there's a lot going on here, and there's a lot of really good stuff in terms of phishing prevention, replay attack prevention. The cryptographics are really sound. The interaction is really important here in terms of that verification and all of these elements. There's a lot that is very, very good within this. So let's look at authentication quickly, and this is a much quicker part. I've highlighted what the differences are, but the workflow is almost identical. Once again, we initiate an authentication, and we get a request options. Same kind of stuff, relying party ID, which is our relying party identifier, challenge bytes, again, to prevent replay attacks. And this time, something different is that we have an allowed credentials list, which says what credentials are allowed to proceed within this operation. So we say, okay, only these ones that you've registered to your account can proceed. And again, we have this user verification option about whether we want no verification must be required or whether we, kind of want it. Now that we've got that, we begin to set up for our client to send this to our navigator credentials.get APIs, and we begin the signature process again. Once again, this is almost identical. We take this data, challenge, origin, must be on, TLS, all of that stuff to prevent phishing. It's collected together, concatenated up, and then sent into the authenticator. Again, we take that, send it to the authenticator, but this time we actually add in the user presence Boolean and the counter state in our signature. So this way we have a signed verification of what the hardware activation counter state is, so that we have a cryptographic signing over that counter. Again, this is another replay defense. And once that signature's happened, of course, that again requires that interaction or that PIN verification to pass. Now that we have that signature, we can begin to return this up to our client. So the client takes that signature, credential ID in the counter, creates this assertion response. We take the assertion response to collect client data, send it to our relying party, and it's going to begin and finalize the authentication. Again, same thing. We take what the server's knowledge of what we wanted to do, and we take the details that we got back from the client, and we verify this. Again, lots of things here. I've cut out a lot. These are some of the important ones. If we have allowed credentials set, we check that what credential was used was actually one of the ones we wanted to be allowed to use here. So they can't just use any random credential that may exist. We check the user verification if it was required. Using the public key that we previously assigned to the user's account, we verify this signature, and this is what does that authentication and the cryptographic element, so that we know that it must be this key that is really authenticating. And then finally, we check that the counter state is always advancing, and if it is, we save that, and if it's not, then we can choose to fail this. So that's authentication, and that's how that works. Again, really similar to registration, but again, there's a lot of really good stuff here. Defenses against replays, domain validation, a lot of authenticity checks around the manufacturer. And this is great, because if we put it back into our scorecard, Webauthn prevents a lot of these attacks that exist today. We prevent, credential stuffing. We prevent phishing, because you must be on the same origin. We prevent, especially with verification. If someone steals your token, they may not be able to use it because it requires extra verification. So there's a lot of stuff that's really good here. But there's always a but. It's a large standard, and there's already there's a lot of ways that in any large standard you can use it incorrectly. There's a lot of dark corners here, and it's a bit of a labyrinth. And many of the issues we will talk about here today have already affected some major identity service providers, and I have responsibly disclosed some of these things to them. They are aware. All of this research was done publicly, so none of this is unknown to the world. First one, the standard doesn't define what the cryptographic challenges should look like. It says that you probably should have 16 bytes, and that they must have enough entropy to make them guessing infeasible, but it's not really strong on this language. And you can very happily send a 1-byte challenge of a 0, and every browser will accept it and pass it to your authenticator. So this basically opens you to replay attacks. And if you are not offering high-quality random challenges, then yeah, you can have replay attacks against auth and registration. Now, looking back at the steps here that were happening during registration, I kind of said something interesting that maybe was overlooked. I said we were looking at the level 2 version of the standard. Well, the level 2 version is undergoing some final ratification before it becomes the version of the standard. The version of the standard publicly today is level 1, which means that these steps don't occur. The steps I have now crossed out are the verification that the algorithm as registered is one of the ones that we actually requested, meaning that the credential is happily able to sign up any algorithm that it wants during registration, provided you support it on the back end. And it also doesn't actually check that you have a platform or cross-platform transport, and it doesn't validate this whatsoever, which means, again, you are free to ignore that and just sign up any credential you want, which can have some interesting consequences given that some of the algorithms supported is things like RSA and SHA-1. Another thing that's worth noting is that even in the level 2 and 3 versions of the standard, this excluded credentials parameter is never actually checked server-side. So this is just free to be ignored by the client. So using this, if you are trying to filter out credentials that have been compromised or things like that, this isn't actually upheld whatsoever. So the client is free to ignore this and just send whatever it wants. And there's starting to be a bit of a theme here, right? There's some really interesting things here also around the replay prevention with the counter. So the signature count on first registration can be 0, which means that the counter will never actually be checked. And the other thing is also that when the standard says some interesting things around what you do if the signature count has gone backwards. The thing it says here is that whether the relying party chooses to update the counter that has moved backwards and save that data or not is up to them. Which means that many relying parties, if implemented incorrectly, if you send them an old challenge, they will update the counter, wind it backwards, and then opens them up to you sending future challenges where the counter state may have advanced. So there's some really interesting stuff where the counter can be replayed here. But a lot of this is really coming down to something, which is that there's a difference between a hint and a requirement in this standard. As you may recall during registration and authentication, the data that we sign is from this relying party ID and this challenge bytes, as well as the origin. However, if you remember, this credential creation options has many more elements than that. All of these are unsigned, which means that the client is free to modify, tamper, and ignore all of them. This is also generally done in JavaScript on the browser. So, this has some interesting consequences during our registration and authentication process. So, once again, we have a live demo. On the left, we have fully updated Chrome and the Webauthn IO demo site, which is a standards-compliant version of Webauthn as produced by Duo Labs. On the right, we have my authenticator, which is set up at the moment with no PIN. We're going to set a PIN on this device. This is what's going to enable user verification to occur, because now that that PIN is set, we can now have this prompted for. We're going to register our account. So we're going to check that the user verification setting is preferred, which means that if you're capable of user verification, you need to provide it. And so we hit register, we add our security key, we enter in our PIN, and as you can see, we enter it in, hit next, and we've now registered our credential. So at this point, we can now begin to attempt to log in. So we begin the login process. We select we want to log in. We'll enter our PIN in, I can't remember which, yeah. We enter the PIN correctly, authenticate, and we've now succeeded. Great. So at this point, we'd believe we've registered an authenticated and verified credential. We do this again. And this time, what we're going to do when we log in is we're going to enter in the incorrect PIN. So we begin to do the login process again. We interact with the key. We enter in the incorrect PIN. And you'll see we get an incorrect PIN warning. We cancel out of this. The authentication has failed. So, once again, we'd believe we have a verified credential here. Let's do this once more. But this time, we're going to pull up the JavaScript Inspector. So we pull up the sources, and we put a break on navigator credentials get, which, as you may recall, is the part which takes the options, which is for the authentication, and then hands it in. We're going to break on this, and when we get it, we're going to edit this properties, and we're going to update its user verification flag to be discouraged. When we set this to discouraged, and we allow our JavaScript to continue, we interact with our key, and we authenticate with no PIN. So, why does this happen? 2 reasons. A registration, the standard states to only store the credential ID and the credential public key. It does not say whether you should store the verification state of the token. And second, a standards-compliant implementation will only check the user verification bit if your outgoing options stated that it was required. This means, with no persistence of user verification result at registration, with no persistence of the user verification policy of registration, and actually not even storing the attestation cert, this assertion is only verifying the user verification bit if you always have required on all of your outgoing messages, and this means that the preferred setting is bypassable if your backend is not going above and beyond the standard to persist the user verification states. And why is this the case? The standard assumes the browser and JavaScript on the site is a fully trusted, uncompromised element of the negotiation. This means that if you are able to modify the JavaScript or the host or tamper with the origin, the browser will just happily do it because it's assumed to be trusted. And part of this comes from the fact that the specification as intended to be used is not the specification as written. The implementers of this standard intended for you to save this user verification information and to do further extended verification, but that is not written in the standard. There is work now occurring within that body to fix this, but it still is going to take some time before that flows out to different deployments and integrators of Webauthn. So, what are our takeaways and effectively homework for everyone? If you're a red team, the core cryptographic elements within Webauthn is sound, but the implementation around it is not always. Really look for user verification preferred or user verification being unset, which implies preferred. This can be bypassed, giving many users a false sense of security that their tokens require verification, and some people may believe that that's actually a policy, meaning that you can downgrade the token from requiring verification to just interaction. So if you can get your hands on one, you've got it. Weak algorithm registration, which may be broken. SHA-1 and RSA is used by a lot of TPMs with Windows Hello because that's all the TPM can offer. Look for poor challenges which can be replayed or reused and may occur frequently. Also look for incorrect counter handling, which again may allow replay attacks, especially if you're registering, if you can tamper with the counter value to be 0, because I believe the counter value isn't signed during registration, then that means that counters will never be checked for that device. And of course, the browser is still a large target for you during any kind of engagement. If you're a relying party, aka implementing this Webauthn standard, just being standards compliant is not enough to be secure. You must persist the user verification boolean and the policy that was used at registration. And you must then subsequently check this boolean for that credential if it's used in the future. This even happens with discouraged, where Apple's Touch ID will always send user verification true, even if you weren't requesting it. And you should be checking that, because if it's not true, something is really wrong with that credential. You must ensure your challenges are coming from a cryptographically secure random number generator and must be 16 bytes or longer. You must check your excluded credentials at registration. If you're excluding them, check that they aren't being used. Assume nothing about a registered device, unless it is from the attestation data or a signed extension. Every other element of this standard is intended to be a hint and guidance to the client on what authenticators the user should select. They are not policy and they are not enforceable. If you're a consumer of Webauthn, so let's say you're consuming an identity service of some kind that uses this, check the JavaScript. If your relying party is offering user verification preferred or no user verification at all, you must pressure them to set this to be either discouraged or required. You must be clear about this, because that way you know exactly how your tokens are being used. Ask if your relying party goes above and beyond this standard, and they're persisting this user verification information, because if they aren't, this may be bypassable. Just being standards compliant is not enough. You really need to understand your security policy requirements, and you must understand what Webauthn can and cannot enforce. The only things you can really check is from that attestation certificate and those signed extensions. Everything else is a hint. And finally, you must protect your authentication site's JavaScript and ensure your browser is updated, because these are assumed to be trusted components in this entire operation. And for everyone, Webauthn is still today, despite its flaws, the most secure and accessible form of cryptographic authentication we have, and it will only continue to improve. So, thank you very much, and I hope that this has been informative.
Your timing was on point.
Yeah.
Questions? Fraser, I knew we'd have one.
Nah, there's no heckling from Fraser allowed.
Thanks, Will. Regarding the attestation certificates, okay, this implies that the relying parties have a set of trusted certificates.
Yep, and that's also something.
Okay.
If the relying party, there is part of the standard, which I didn't go over, which is that there is actually a list of places where you can get those, certificate origins from, and the CAs and things like that. And of course, again, the relying party may also not do this properly, and so can you really trust that attestation?
Right. And so my question is about onboarding, and curation. Who actually creates these trusted sets? It's basically like a CA trust store.
The vendor of that token will issue, and it will say, okay, I'm publishing my tokens that they are doing U2F attestation. And then it will publish its CA chain, and then that will be sent to the FIDO Alliance, which is the standards body that governs whether a token is FIDO compliant or not. And then they hold that list of the CAs, and then that way you can access that, and then you get that information, and then you can use that to build up your trust chain. So the FIDO Alliance, or the W3C, is really kind of the CA group, but but the manufacturers are what actually does that, creating that chain. And so, yeah.
Good, mate. A good presentation. I mean, it might be a little bit unrelated, but do you see this technology coming to phones at any time?
To what?
Phones, yeah, mobile phones. For you
it's already there.
Could I use my iPhone as a hardware key to?
It's already in the standard. Touch ID is already supported.
Sorry, I mean, could I use on my laptop?
Yeah, your laptop's Touch ID is supported too.
Could I use my phone as the hardware key on my laptop?
So as in you can use your phone to authenticate an operation on your laptop?
Yes.
That would be relying party specific behavior. This is not about, can I use my phone to authenticate something on my laptop? This is about saying, I've logged into my phone, my device can now continue to authenticate on my behalf with cryptographic auth. Whether your device that you have is doing cryptographic auth and then says, oh, that means my other device can then proceed, that's a relying party specific thing, and that is, up to that. But, again, at that point, it's kind of like, well, if your laptop also has a cryptographic code processor, why do you need your phone's one to do the same operation that your secure enclave on or your TPM on your machine could do? Because that device is continuing to authenticate on your behalf. So, that would be relying party specific behavior though, yeah.
Okay, cool, thank you.
Yeah, good talk. Can something like this be have 2FA in addition to that? So you have your token key that you have with you and still generate the code on your phone or something like that?
Yeah, absolutely. The workflow that a relying party wants to go through in terms of that, offering that authentication, that's completely up to you. You can still say want to have a password first, or maybe you have your Webauthn first, and then maybe you have a TOTP as well. You can have it so maybe you have just the user verified token for Touch ID. Maybe that's sufficient for your policy. Maybe that's not. Maybe you need a password and the user verified token. It depends on how many factors you want, all of this stuff. Again, that is behavior and policy that you can configure as a relying party or an auth provider. And many auth providers can do this. So it really comes down to what your needs are and what you want. I would expect to see that there are websites which begin to just have unverified Webauthn as the sole factor of authentication, because that's already lifting the bar so much higher than what we have with passwords. But I can also see high security environments requiring not only a verified Webauthn token and probably with a discoverable key. There's something I didn't cover here, which is to do with where the keys are, whether it's in the token or whether it's discoverable or whatever. But yeah, you can have that key non-discoverable, discoverable in this case, and yeah, the terminology is so confusing. It's discoverable. Discoverable keys means that they can't be extracted and known, whereas non-discoverable are key-wrapped keys where the credential ID is actually an encrypted format of the key, and then you've got to give it back to the authenticator before it can even do the authentication. But the terminology is completely backwards to what you think, because you hear discoverable, what do you mean you can steal my credential? And it's not. It actually means you can't steal this one, whereas non-discoverable means you can absolutely steal this one if you...
Round of applause for Will, come on.
Yeah.
Awesome, thank you.